Hi everyone. We are going to be discussing the next generation science standards for elementary educators. The next generation science standards are recognized nationally. Every single state has adopted their state standards from the next generation science standards. So if you ever have questions about your state standards and can't find the resources you need, you can always Google the next generation science standards and get this almost identical information. So what exactly are the next generation science standards? They're made up of 3 dimensions. So the dimensions are science and engineering practices, disciplinary core ideas, and cross-cutting concepts. And this rests on a view of science as both a body of knowledge and an evidence-based model and theory building expertise, aka we are going to do science, not just listen and watch science. It continually extends, refines, and revises knowledge, and it presents 3 dimensions that will be combined to form each standard. So as you can see here, when we combine our science and engineering practices, core ideas, and cross-cutting concepts, then we come up with the standard. So you're probably thinking, what the heck are you talking about? So this is an example of the Louisiana State Standard 3-PS2-2. This is a 3rd grade physical science state standard, and it is in the unit of motion and stability, where students are going to learn about forces and interactions. You will see the standard itself is considered the performance expectation, and that's where they're going to make observations and or measurements of an object's motion to provide evidence that a pattern can be used to predict future motion. Now, as an elementary school teacher, you have to be a subject matter expert in ELA, math, science, and social studies. And sometimes there's going to be areas of science where we're not really sure what they're asking of us in the performance expectation. And that's why the state provides a clarification statement. And the clarification statement is always going to be an example. So here you see examples of motion with a predictable pattern could include a child swinging in a swing, a ball rolling back and forth in a bowl, or 2 children on a seesaw. And then below that, you will see the 3 dimensions that the state expects you to hit on as you are teaching this concept. The first one is the science and engineering practice. There are 8 of these practices. Each standard only highlights one. As you can see in this one, there's only one bolded. And this one's called planning and carrying out investigations. The way I think about science and engineering practices is this is what I want my students to be able to do. The next one is a disciplinary core idea. In this case, they're explaining what they want your students to be able to know. So think of science and engineering practices as doing, and disciplinary core ideas is what we want our students to be able to know by the end of this unit. And cross-cutting concepts is this idea of something that you can apply to other scientific disciplines and other disciplines. In this case, patterns. So let's break down each of these 3 dimensions so you can better understand them. The first ones we're going to break down are science and engineering practices. Think skills, or what we want our students to be able to do in science. It describes behaviors that scientists engage in as they investigate and build models and theories about the natural world. The key set of engineering practices that engineers use as they design and build models. And there are 8 different types of practices. Don't worry, you're not expected to know and do all 8 different types of practices in each standard, but rather each standard has one of these practices in it. So for example, the first science and engineering practice, or SEP, is asking questions for science and defining problems for engineering. And as you can see in this chart, our expectations of what we think our students should be able to do in kindergarten to 2nd grade is going to be different than 3rd through 5th grade. So, for example, we expect that our students will be able to ask questions and define problems despite the grade that they are in. However, in kindergarten, we want our students to be able to ask and or identify questions that can be answered by an investigation. That means that we might ask our students to contribute a whole bunch of questions to the board around a particular phenomenon. But in 3rd to 5th grade, we want our students to be able to not only throw out a whole bunch of questions, but then be able to identify scientific testable and non-scientific testable questions as well. All right, let's keep moving on. So here is an example. I give you a lesson plan for a 3rd grade life science where we want our students to be able to analyze and interpret data to provide evidence that plants and animals have traits inherited from parents. That variation of these traits exists in a group of similar organisms. And when you open up this lesson plan, what you will see is that we are asking our students to ask questions about what they're observing and start to figure out how can we group these different organisms and what's the best way to test our ideas of how organisms get the colors and features that they have. The second science and engineering practice is developing and using models. And if you watch this YouTube video, you'll see a terrific lesson in which a teacher is using models. Now, I know what you're thinking, Hollander, my kids are in 1st grade. What kind of models do you expect them to construct? What's great is that a model doesn't have to be something that's 3-dimensional. Models could be diagrams or drawings. They could be physical replicas or mathematical representations. They could be analogies. And then there's so many computer simulations that are out there now, particularly because of the COVID-19 pandemic. Modeling tools are used to develop questions, predictions, and explanations, analyze and identify flaws in systems, and communicate ideas. What's really great is, and what we're seeing a lot of in the scripted curriculum, is that we have our students create a model, and then as they obtain more information or learn various scientific concepts, they then go back and revise that model until they get to a point where they feel confident in their model. So again, we can break the science and engineering practice up between our lower level elementary and higher level elementary school students. And you can see some key differences between the two. I think what's interesting is we want our kindergarten through 2nd graders to be able to distinguish between a model and an actual object, whereas when we get to 3rd and 5th grade, we're trying to have them identify the limitations of a model. The third science and engineering practice that I think most of us are most familiar with are planning and carrying out investigations. Students should have opportunities to plan and carry out several different kinds of investigations during their K-12 years. At all levels, they should engage in investigations that range from those structured by the teacher in order to expose them to a problem or issue or a different type of method, to ones in which they explore on their own. I am a huge proponent of having your students investigate their own questions and develop their own investigations. Again, we can see that there's distinct differences between our kindergarten through 2nd grade and 3rd through 5th grade students. For example, in kindergarten through 2nd grade, they will need a lot more guidance with both planning and conducting an investigation. Whereas your students might need more guidance on how to evaluate the appropriate methods in our tools for collecting data in 3rd through 5th grade. If you have an opportunity, I highly recommend you watch this investigation. It's about apple browning. It's terrific. It's with younger learners in which they investigate what would prevent an apple from browning. And it goes through the steps of the scientific process and helps students to create an investigation around such a simple natural phenomenon. The next science and engineering practice that we want our students to be able to do is analyze and interpret data. Once collected, data must be presented in a form that can reveal any patterns or relationships and that allows results to be communicated to others. Most raw data has little meaning. However, we can help our students organize and interpret data through graphing and statistical analysis, which will bring meaning to the data. Again, we're going to see much different uses of the science and engineering practice in our lower elementary students versus our higher elementary students. For example, we want to use information from observations to construct an evidence-based account of a natural phenomenon and then collect that data to understand it. Whereas in a 3rd through 5th grade class, we need our students to use evidence like measurements and patterns. Some terrific state standards that use analyzing and interpreting data are going to be things like materials that are best suited for specific purposes. For example, you may have in 5th grade created a solar oven and you got to use whatever materials you wanted to see whose nachos could cook the fastest. Or maybe you were dropping eggs from the top of a school building roof to determine what materials would prevent that egg from breaking. Another great use for this science and engineering practice is with weather data. Another science and engineering practice is using mathematics and computational thinking. Now I know what you're thinking. How am I going to get my 1st grader to think computationally? I felt the same way. Students are expected to use math to represent physical variables and the relationships and to make quantitative predictions. Remember how I mentioned how the last science and engineering practice would be terrific for weather? So with this one, I'm a huge proponent of thinking of weather data when I'm thinking about the science and engineering practice. Here in kindergarten through 2nd grade, we want our students to be able to decide when to use qualitative versus quantitative data and use counting and numbers to identify and describe patterns. Whereas in our 3rd through 5th grades, we want to decide if qualitative or quantitative data are best to determine whether a proposed object or tool meets the criteria for success. And we want our students to be able to organize simple data sets to reveal patterns that suggest relationships. Another science and engineering practice, number 6, is constructing explanations and designing solutions. We need to ask our students to demonstrate their own understanding of the scientific idea by developing their own explanations of a phenomenon. Whether based on observations they've made or models they've developed, we want them to engage in a discussion. And here's a terrific YouTube video showcasing exactly how to do that. We want our students to use information from observations to construct evidence-based accounts of natural phenomenon. We also want them to be able to identify the evidence that supports a particular point in explanation. How many of us have heard of CERs? Aren't those on the LEAP exams? Where we want them to explain things and use evidence and reasoning. This is where we're building off of that. The next science and engineering practice is engaging in argument from evidence. Many of our students are not trained on how to support their ideas using evidence. Again, we're coming back to that CER idea. We want our students to be able to reach agreements about explanations and design solutions. They will one day be out in the workforce and they're going to have to learn to work together and express their ideas and come up with conclusions together. Here's a terrific example. Young students can begin by constructing an argument for their own interpretation of the phenomenon they observe and of any data they collect. They need instructional support to go beyond simply making claims, and that is to include reasons or references to evidence to begin to distinguish the evidence from opinion. And I have this terrific website called the Argumentation Toolkit, and it helps our students understand how to discuss differences in ideas and how to use evidence and reasoning to discuss those differences in ideas until they can come up with an idea that they can all agree upon. And then lastly, we have science and engineering practice number 8, and I think this is one of the most important ones today, and that's obtaining, evaluating, and communicating information. We want our students to be able to start to learn how to read like scientists, interpret data and information like scientists, and be able to write and speak like scientists. And that takes practice. We also want our students to be critical consumers of information about science. We want our students to leave our classrooms and not believe everything they hear from their siblings or what they see on Facebook or TikTok or Instagram. We want them to be able to distinguish what is good scientific claims and what are not good scientific claims. So this is kind of tough in a K through 2 classroom. I highly recommend that you're reading grade appropriate texts and having them evaluate grade appropriate evidence, but also you could have them draw pictures and explain in their own words the phenomena that they're observing and the conclusions that they're drawing. I think in 3rd through 5th grade, that's when we can start including more scientific writing, if that's writing lab reports or explanations, and having them have to talk like scientists using specific language that they're learning to describe various scientific phenomenon. Now, as you observed in the Louisiana Science Standards, after that science and engineering practice, you saw cross-cutting concepts. These cross-cutting concepts have applications across all domains of science. As such, they're a way of linking the different domains of science. So they include patterns, similarity and diversity, cause and effect, scale and proportion and quantity, systems and system models, energy and matter, structure and function, and stability and change. And then finally, what we want our students to know, or our disciplinary core ideas, can be grouped into 4 domains. And what you'll notice is in every single elementary grade level, those domains are going to be taught in some level. So every 3rd grade class is going to learn some life science, some physical science, some earth and space sciences, and some engineering, technology, and application sciences. And we scaffold on these DCIs. So what they learn in life science in 3rd grade, they may revisit, but at a deeper and more sophisticated level in 5th grade or 9th grade. The disciplinary core ideas have the power to focus our curriculum, our instruction, and our assessment. Remember backwards design. We are first going to understand what it is, the specific objectives that we want our students to learn. In this case, that would be that disciplinary core idea you saw in the standard. Then you want to build out your assessment and then figure out how are you going to have your students learn this information. What activity or science and engineering practice are we going to use to meet this DCI? It's going to have broad importance across multiple sciences, and it's going to provide a key tool for understanding or investigating more complex ideas. It also needs to be teachable and learnable over multiple grades. So as the students progress in their elementary school curriculum, they will increase both their levels of depth and sophistication. I just threw a lot at you in the last 18 minutes, and this is a terrific summary video using someone else's words to describe the next generation science standards. Now let's go back and revisit that science standard in motion stability 3-PS2-2, where we want our students to be able to make observations and/or measurements of an object's motion to provide evidence that a pattern can be used to predict future motion. As seen below, you can see that the science and engineering practice that this standard wants you to focus on is planning and carrying out an investigation. And what we want our students to actually know, or the disciplinary core idea, is that patterns of an object's motion in various situations can be observed and measured. When the past motion exhibits a regular pattern, then students can predict the future motion. Technical terms such as magnitude, velocity, momentum don't need to be taught at this level. However, the ideas and concepts of these may be introduced. And then the cross-cutting concept that will link this to other scientific disciplines is patterns of change can be used to make predictions. So this week's assignment is I want you to pick up a Louisiana State Standard and break it down. Most elementary schools require that we have an I can statement, so consider what your I can statement might be. Please make it grade appropriate. Tell me what that means. Tell me what the science and engineering practice is for this particular standard, what the disciplinary core idea is, and the cross-cutting concept. Then in your own words, tell me exactly what that means.